Today I want to show you another application of the Primal-Dual scheme, here for the problem of computing minimum Steiner forests. So what's the problem? We have a graph G, we have edge costs, and we have a set of pairs of terminals. So we have S1, T1 up to SK, TK. So here we have our graph with edge weights, and now we also have terminals. And the goal is to find a graph of minimum cost that connects those pairs of terminals. So let's formalize that. So we want to find a set of edges of minimum total cost such that the subgraph that we obtain connects every pair of terminals. So S1 and T1 should be connected in the subgraph, S2 and T2, S3 and T3. But we do not, for instance, we do not need to connect S1 and T3. So those could be in different components, just S1 and T1 need to be S2 and T2 and S3 and T3. So what is a minimum Steiner forest in this example? So here you see it. So we have here a tree, here another tree, but there's no need to connect this tree here, which is in our case only an edge, with the rest of the tree, because we have S1 and T1 being connected, S2 and T2 are connected, and S3 and T3 are also connected. There are some special cases of this problem that are worth mentioning. For instance, the shortest path problem is the Steiner forest problem, where we only have one pair of terminals, because then this minimum graph is simply the shortest path. If I simply make all of the vertices terminals and ask for a graph that connects all of the pairs of terminals or vertices, then I get the minimum spanning tree problem. If I simply have a set of terminals and within that set say I want to have all of them connected, then I end up with the minimum Steiner tree problem. So these are all special cases of the minimum Steiner forest problem. So given those special cases, one might think about whether any of those is useful to actually get an algorithm for the minimum Steiner forest problem. So let's have a look at that. So for instance, we could imagine computing K shortest path. So for every pair Si, Ti, we compute the shortest path, and then I simply take the union of all of those graphs. We could also imagine simply taking the Steiner tree and hope that it's not much larger than the Steiner forest. But both of those approaches perform poorly, and you might want to think about this sketch for yourself. First, an example of why that is the case. So let's look at this first one. So why do K shortest path not give a good solution to this problem? So here I have K shortest path. If I sum those weights up, I get a weight of K. But let's say I also have the following vertices. So I have two additional vertices. All of these have a distance epsilon. So all Si have a distance epsilon to one of those two vertices and the Ti to the other one. And now I have an edge with cost 1 between those two. Then the shortest path remains what it is for each of the Si, Ti, but the minimum Steiner tree, and minimum Steiner forest, has weight essentially something with epsilon plus 1, so it is significantly smaller. For the Steiner tree, so minimum Steiner tree problem, why is that not a good idea? So let's say this is a minimum Steiner forest, and the only way to connect those two components is a very long edge. Then obviously we would not want to add it. So there, the difficulty is actually figuring out which terminals should end up in the same trees of the forest. So those approaches we cannot use. What we're going to be able to use is Primal-Dual. For that, we first need to formulate the minimum Steiner forest problem as an ILP and then dualize it. So let's do that. So what is an ILP, or what is a ILP for the minimum Steiner forest? So our choices are taking edges, yes or no. So we will want to have variables for the edges, 0, 1 variables. And if we have that, then the objective function is also easy to formulate, because I simply pay the cost of the edges that I select. So those where I set the variable to 1, and this simply boils down to the sum of edge cost times the variable for that edge, because that is 1 if I pick it, or 0 if I don't do so. So but now we have to ensure connectedness. And this is not quite as simple. So if you've seen some ILPs for shortest path flow and similar things, then you might think of formulating this similar to flow. To some extent we do this, but we go to the dual problem, so we use cuts. Yeah, so let's see how that looks like. So here we have a pair SI-TI, and let's say I have now a subset of the vertices that contains SI but not TI. Then to guarantee connectedness, we will need to have an edge from a vertex in the set that actually goes to a vertex outside of that edge, because otherwise SI and TI would be in different components. Yeah, so one of those edges I would need to select those. I call delta S, if this is my set S, delta S is the set of edges with one vertex in the component, one outside. I should select one of those, so let's say that one. That means what I want to have is this constraint. So I want to have, if I take the sum of edges out of delta S, so the edges that go out of this component, I want to select at least one, meaning the sum of those XE should be at least one. And I want to have this for all components with SI in it and TI outside, or TI in it and SI outside. So this is my big SI. This is defined as simply the components with only one of those two. And so these are cuts separating SI and TI. And the delta S are then the corresponding cut edges. So why does this now enforce connectedness? You can argue this in different ways. You could argue incrementally, so more like an induction. And you're saying I start at SI and then I will find an edge. So I take that component, I know there's an edge going out, and I can continue incrementally until I reach TI, and I know that I can always continue because there's always an edge, a further edge, as long as I have not yet reached TI. You could also prove this simply by contradiction, essentially concluding that if you don't have connectedness, then these need to be in different connected components. You take one of the components and there has to be an edge out of that component, and that gives you your contradiction. Okay, so we know that this is a suitable ILP. I mean, suitable I have to be a bit careful with because it has to also be useful. And at first this doesn't look that useful because we have lots of sets here. So we have an exponential number of constraints. So this ILP would not be useful, or at least not directly, if we would want to do something like LP relaxation. But we're only using the ILP here as a tool to design our algorithm. And for that, as you will see, it is actually very useful. So that's our ILP. Now we want to dualize it. In the dual, we will, instead of minimize, we're going to maximize for every primal constraints. So here we have a constraint. We will have a dual variable. So this variable ys, meaning that for every such set, we will have a variable s. So that's our setting so far. Now, what is the function that we need to maximize? Now, simply doing dualization. This is the C vector for the primal, so a vector of ones. This now becomes the coefficients in the objective function. So I'm going to sum over all of the cuts and then simply ys. And now for every variable in the primal, I get a dual constraint, and the bound. So the b in the dual corresponds to the c, so the coefficients in the objective function in the primal. So what I get here is simply for every, so here we had the variables, for every edge a variable, now we have for every edge a constraint, and we're looking at the sum of cuts that contain that edge, summing up their ys, and this should be at most CE. And if you've seen the video about set cover, you will recognize this as a pair of a covering LP and a packing LP. So for set cover, the primal had very much this structure also, and we called it covering LP, and then the corresponding dual packing LP, and packing because I want to make ys as large as possible so that I can still pack it within this cost of CE. Here there's also another nice intuition for the dual, and that is the following. If we see our graph, a primal graph, or the graph that we're considering, as a graph of a network of bridges, then we can think of the dual variables as modes. So here we have a bridge, there's a mode. So let me have that in a more abstract example. So this is a cut, and I'm interpreting it as a mode which goes below those bridges. And this, how large I make y is, this is the width of this mode. We interpret now delta s as the set of bridges over the mode around s, and the dual variable ys is the width of that mode. And if I now, let's have another example, if I now consider different sets S, then I get lots of modes. So here the S is simply this vertex, only one vertex. I'll have a mode around that, and I could also have those two as a set, and then I have a mode around those two, and so on. And the interpretation then of this constraint is to say, I'm building modes. I want to increase the sum of width as far as possible, but beneath each bridge, I mean the width of the modes under that bridge cannot be overall wider than the bridge itself. So that's an interpretation which we will be using later once more. So we've seen the Primal-Dual method for set cover, at least I assume so. You don't have to have seen it, but I would recommend watching that video first. And there we used complementary slackness. Actually, there we used relaxed complementary slackness. Now, for now, we just need complementary slackness in this problem. And what was that again? So we have a pair of a primal and a dual problem. Again, we assume that our primal problem is a minimization problem, then the dual is a maximization problem. And then the complementary slackness tells us the following. If I have a solution to the primal and a solution to the dual problem, so a valid solution, then those x and y are optimal if and only if I have primal and dual complementary slackness. Complementary slackness means that either primal complementary slackness, either a variable is 0 or there's no slack in the corresponding dual constraint. This is a variable in the primal that corresponds to a constraint in the dual. The constraint is this term should be smaller equal Cj. No slack means it actually holds with equality. Either this is 0 or the dual constraint holds with equality. And likewise in the dual, yi is 0 or the corresponding primal constraints holds with equality. So x and y are optimal if and only if I have these conditions. If and only if complementary slackness holds. Complementary slackness is a key tool in the Primal-Dual approach. So we will be, for this algorithm, guaranteeing primal complementary slackness. So what does that mean? If a variable corresponding to an edge is non-zero, we will only set a variable to something non-zero, to 1 actually, if I have complementary slackness. So if the corresponding dual constraint, I have equality here, so the ys are sufficiently large. And such edges, so if I have complementary slackness here, such edges I will call critical edges. So the Primal-Dual approach says I'm only going to pick critical edges. And now the idea is that we're going to start with a trivial assignment to the variables, which gives us a feasible dual solution, but an infeasible primal solution. And then we are iteratively improving this solution. So we're iteratively making the primal problem more feasible by also, in particular, keeping it integral, and also change the dual solution on the way. And this, so the key here is a complementary slackness. And then eventually, when our primal solution is feasible and integral, and we have this complementary slackness, then we will be able to give some approximation guarantee. In such an approach, we will need to be able to identify primal constraints that are violated. So, and primal constraints that are violated, so I want to eventually have that for every cut, the sum of edges, or the sum of cut edges is at least 1, because that means I've selected one, or at least in the ILP, it would mean that we've selected one. And how do we find those constraints? We will do so by considering the connected components for each of the SITI, and restrict ourselves there obviously to those where there's one I such that the connected component only contains SI, or it only contains TI but not the other one. And then how do we improve the dual solution? Yeah, so we're going to increase the Ys for those components until some edge becomes critical. So let's try this first in a rather naive approach, which actually will not give us the guarantees that we want to have, but from which we can then learn how to do it better. So this I now call naive algorithm. This will not be our final algorithm, but this is simply Primal-Dual very directly applied here. We set all of the Ys to 0. Initially, we haven't any edges selected into our forest, so F is the empty set. So what we're going to do is, while there is a pair that is not yet connected in the graph that I get by taking those edges, I'm picking one component in the current graph such that only Si or Ti is contained in it for some I. And for that component, I'm going to increase the corresponding dual variable, Yc. And how far do I do that? I do that until one of the edges, one of the cut edges becomes critical. So for one of the edges, I have that this sum here becomes equal to the corresponding edge cost. And at that point, I'm going to simply take that edge, add it to F. And that is it. Now, we should say one thing about running time at least, and that is the following. Of course, we have an exponential number of constraints, but we don't need to keep track of all of them. Yeah, so all of the constraints where the Y is still 0, I can handle implicitly. I mean, if I didn't say anything, it is simply still 0. So let's see how well this algorithm performs. So the cost of the solution is this here, the sum of the CE. And now we can make use of the fact that we are guaranteeing primal complementary slackness, because I now know that the CE is equal to this sum here. Yeah, so this is exactly what primal complementary slackness gives me, that there's no slack in the corresponding dual constraint, and the corresponding dual constraint is that this here is smaller equal CE. So we know here we actually have equality, so I can simply replace CE by this sum. Now let me rewrite this sum slightly to make it a bit simpler. So what I have here, if I look at YS, So for which edges do I have ys here? I have it for the edges that are in the cut and in the forest. I can rearrange the sum to say I'm summing over all of the cuts, ys times how often it occurs in the sum, and that is number of edges that are in the cut and in the forest. Now this is a guarantee that we get for the cost of the solution, and for the approximation factor we're going to compare that to the value of the dual solution. The value of the dual solution is simply the sum of the ys. And what you see here is that this doesn't quite work out yet, because the approximation factor is this term here, and that term can actually not be reasonably bounded. So this can be as large as k, the number of terminal pairs. And here's an example where it actually gets that bad. So let's say this vertex corresponds to all of the Si, and here we have the various terminals. Let's assume the algorithm starts with the component that contains the Si. Then I'm growing the corresponding dual variable until one edge becomes critical. So all of the edge costs here are assumed to be 1. So actually all of the outgoing edges at the same time, namely when ys is 1, become critical. And I end up picking exactly this as a graph. That as such is not that bad in this example, because the graph is okay. We were going to see that it actually can get worse. But in terms of the approximation guarantee that we get, we have that this term for this ys, so the intersection of f with the cut edges, that's simply all of the edges here. And so there we indeed get a k. Now the problem is that this component carries all of the costs. At least that's one of the problems. So the natural question would be, how can we distribute those costs better? And we have more components. So essentially we have one component per terminal initially. So we have all of these components. And what we want to do is to make sure that the costs, so the y, what I put onto the y, is better or more equally distributed over those components. And we will achieve this by increasing all of the y's simultaneously. This will also help us in particular with the following. So let's look again at this example here and imagine you're allowed to change the edge weights. So far this forest that we got is actually not that bad. It's just possible, I mean, it's actually optimal, but with appropriate edge weights, it can be actually very bad. So can you think of how to choose edge weights here to make this example also bad in terms of the approximation factor? So what we can do is simply, we make all of these edges, we give them a cost of epsilon. Those still have a cost of 1. And now again, the algorithm would proceed just as before because it doesn't know about those epsilons. So it would again pick the same tree, but there would have been a much smaller one where I maybe take one of those green edges and then lots of epsilon edges. So this is also off by a factor of k in that way. But again, if we simultaneously increase all of the components, then we would earlier pick the ones with epsilons. So the synchronous increase will also help us there. So let's look at that as an algorithm. So this is now the algorithm that we are considering. So again, we start off with setting all the y to 0. We have so far no edges in our forest. We also have this L variable. So while I still have disconnected Sj, Tj pairs, what do? I maintain a set of active sets, I call this. Active sets are the components in my current graph, such that this component for some I only contains Si or Ti. Those are the active components. So those are the sets where I still need outgoing edges. And for all of these components, I'm going to increase Yc at the same time to the same value. And I do so until there is some edge for which I get complementary slackness, where I get that the dual constraints holds with equality. And then I'm going to pick that edge, add it to my set of forest edges. So now instead of increasing some arbitrary YC, we're doing all of them in the same time, and this will help us. What we will also need to do is we take the solution that we get at the end and remove edges that are not needed. What do I mean by that? So I go through all of the edges, and this was now why I also maintain this L, although actually, strictly speaking, wouldn't have been necessary. But this numbers, in this way, have numbered my edges. And now I go through the set of edges, and if removing an edge leaves the solution feasible, so keeps all of these pairs still connected, then I'm going to simply remove the edge. And I go through all edges, see whether I can remove them, do so if I can, and then eventually return the result. The result I'm going to call F prime. Yeah, so for the analysis, it's important. F is the set of edges while I'm running the algorithm before pruning, and then at the very end, I'm going to call that F prime. So that will show up in the analysis several times. Let's look at this by an example. And we have 6 vertices, and we assume this is an example in the plane, and the edge costs actually correspond to the distances, the Euclidean distances. Now I'm increasing all of the YC simultaneously. So initially, because each of these is actually a terminal, I have these 6 components. So all six I'm going to increase the YC simultaneously until some edge becomes critical. And this would be the moment in time where one edge becomes critical. Now I'm going to add that edge to my tree and continue. So now I'm in the next iteration of my loop. And now my components are the same as before, just that these two are in one component. And I'm now taking all of those YC, all increase them until one of the edges again becomes critical. I'm going to pick it, and so on. So this is the graph I end up with. So this is my F at the end. But now I still go through all of the edges and check whether I can remove them. Here I can remove exactly one edge, this one here. So this one I'm going to remove here. And now that is a solution of the algorithm. We will now want to prove that this is actually a good solution in terms of its approximation guarantee. First, let's make some structure observations, beginning with the following lemma. If I look at my active sets, so that is the set of all of the components which only, for some I only contain Si or Ti. And then summing over all of those components, the number of edges, the cut edges that are also in the final tree, I can bound this by 2 times the size of the active set. And this 2 will be important. Before we prove this, let's build some intuition. So here we have a set of vertices. Let's say we are somewhere in our algorithm. So in some iteration, these are the connected components that we currently have. And now let's classify the edges. So we have edges that are in the final forest within those components. So let's say in those edges here. Then we will have actually also more edges in here possibly, which are not in the final forest because I'm removing them in the pruning step, but they exist at this moment in time. So that might be, for instance, this one here. Could be that it's connecting those 2 vertices, but at the end I'm going to remove that edge in the pruning step. And then there are edges that are not yet there, but that are in the final forest. And those, the edges that are missing so far, those are edges that go over cuts of the current components. So this could be this set of edges here. Now this is what shows up in the sum up there. And we want to show that there are not too many of those. So what we essentially want to show, if you look at this, is that for each of the active sets of the components that still need to connect, so for each of those, on average, I should have at most 2 edges. Yeah, so degree of these components, degree as in outgoing edges, should be on average at most 2. Now, since we have a forest, this actually holds. So the degree is at most 2. But there is a catch, and that is what we have to handle in the proof, and that is the following. Not all of these components are active sets, or don't need to be active sets. So it could be that this component here is perfectly happy. There's no I such that this only contains Si or Ti. So this component per se does not have to go, but it's still in my average. So now imagine this component having a degree of 1. Then that would mean that the knowledge that I have an average degree of 2 doesn't help me, because taking out that component might increase the average degree on the remaining ones. That's what we have to handle in our proof. So let's say we have the edges EI added in that order, E1 up to, and we are in iteration I, so up to EI. So this is my current set of edges, which I now call Fi. The corresponding graph I call Gi. Gi star is the graph that I get by also adding the edges that are in the final forest, but not yet here. So the edges that I'm actually interested in. And we're actually interested in these edges. We're actually not interested in what happens in these components. So I'm going to contract all of those components to a vertex and have then edges between those vertices. And this I call Gi prime. So that's the graph I'm going to consider. That looks like that here. And to simplify the graph further, I'm going to ignore components that don't have in or outgoing edges. So even if I take those components out, this vertex here, if I take it out, the rest is a forest. So for the rest, I would still need to make this estimate successfully, that taking the active ones, the active components in that set, those have an average degree of smaller equal to. I mean, that's what we want to show. So I'm going to take out that vertex. And the remainder, so the Gi prime that I now get, is a forest. Thus, if I now sum up over the components in this graph here, Gi star, and count the number of cut edges that are eventually in F prime, so corresponds to the edges. So for this component, this edge I'm counting, this corresponds to the sum of the degrees in this graph. Yeah, so this one gets 1, this one 1, 2, 3, this one again 1, and this is the same here, 3, 1, 1, 1. And the sum of the degrees I can rewrite using the hand-checking lemma as 2 times the number of edges. This corresponds to 2 times the number of edges in this graph here. This graph, since it's a forest, 2 times the number of edges is at most 2 times the number of vertices. So this is a bound that we now have so far. We somehow have to handle the fact that there are components that are not active in the sense that they don't contain a pair like this. So this is an active component because I need an outgoing edge, and this one too, I need an outgoing edge. And let's say these two are also active. I mean, this one I already know is active, but this one is also active. We have these active components, and in my example, we also have an inactive component. So this component is perfectly happy as it is. Now, the missing piece in our puzzle is the following. Inactive components have degree at least 2. So what this says is inactive components cannot have a degree of 1. Because degree 0, we would have removed it already. So degree 0, it doesn't count. Saying degree at least 2 means it does not have degree 1. And why is that the case? So imagine you have an inactive component that would have a degree of 1. The only reason I still have this edge here is that the edge is necessary, because otherwise, if that edge wouldn't be needed, I would have removed it in the pruning. But this edge is not needed because this component is happy as it is. And if this component only has a degree of 1, this edge can also not help someone on the other side here because you get stuck in that component. Yeah, so if I have an edge here, I also need to have a second edge that goes out. So this would actually, in my example, happen. And that means I have at least a degree of 2. But if inactive components have a degree of at least 2, then I can say that the sum of the degrees of the active components, this is now, I'm going to make use of this fact here. So this is sum over everything, over all components. I know that this is smaller or equal to 2 times the number of vertices. Now I'm subtracting, so I'm taking out of the sum of the degrees of the inactive components, and I'm putting them onto the other side. So then I have minus that sum here. And because the degrees are at least 2, this is smaller or equal minus 2 times the number of inactive components. Because each of the inactive components, the summand here is the degree, and the degree we know is at least 2. But this now is 2 times the number of all vertices minus the inactive ones. Yeah, that is 2 times the number of active ones, and this is 2 times the size of the active set. And this proves my lemma, because this sum of the degrees is corresponds to this sum here, and we have now proven that that is at most 2 times the number of active sets. With this structural lemma, we can now prove that the algorithm that we designed is actually a true approximation. So that's stated in the following theorem. The Primal-Dual algorithm with synchronized increases gives us a true approximation for the Minimum Steiner Forest Problem. We start the proof again by an estimate that we already had, which used complementary slackness. So this is the cost of the solution. Complementary slackness gave us that we can write it as, first of all, that sum. But this was the one that we already considered for the first naive algorithm, and that equation as such does not change. So we have that the sum of the costs we can write as a sum over the cuts, and then number of cut edges that actually end up in f prime. And we will prove by induction that this sum here, that during the algorithm, at any time in the algorithm, this is at most 2 times, and then the sum of the dual variables. And with that, if we have that, this immediately implies the theorem, because I then have that the cost of my solution equals this term here. It's at most twice as large as the objective value of this dual solution. And the dual solution is a lower bound for the optimal solution. So we have an approximation factor of 2. And this we're going to prove by induction. We want to prove this inequality by induction over the iterations of the algorithm. Initially all of the y's are 0. Then that's our base case. And in that case, this inequality trivial holds because each summand has a y. So we have here simply 0 smaller equals 0. Now let's assume the inequality holds at the beginning, the start of some iteration. So in that iteration, we're going to increase all of the y's for the active components by the same amount. Let's call that amount epsilon. How do the two sides of this inequality change? So on the left-hand side, in each summand, I have a y, which increases by epsilon. So the total increase is epsilon times this sum here. On the right-hand side, I also have a y in each of the components. Each of these increases by epsilon, so the total increase is 2 times epsilon times number of active components. So that's 2 times a times epsilon. On both sides, I have this factor epsilon. Here I have the sum, here I have 2a. But the structural lemma exactly says that this term here, the left-hand side, is smaller or equal to the right-hand side. And then on both sides, factor epsilon. So the increase on the left-hand side is smaller or equal to the increase on the right-hand side. So if initially I had the inequality, I now still have the inequality. So what have we seen? We've seen the Primal-Dual algorithm with synchronized increases. And this approach of synchronized increases, this also applies to other problems. And this circumvented the problem of making a bad choice of which dual variable to increase first. This gives a true approximation for the Minimum Steiner Forest problem. We should, of course, ask ourselves whether the analysis is tight, and indeed the analysis is tight. Here's an example. So here we have sets or terminals S1, S2, and so on, terminals T2, T3, and so on, and one extra vertex. So here we have this tree as an option. So those all get weight 1. But the other edges, so I have this blue tree, but the other edges get weight 2 minus epsilon. And now if I start increasing the dual variables, they will actually stop at 2 minus epsilon half. Because at that point, because each of these edges, I mean such an edge here, includes 2 of the terminals, at that point the y values will add up to the cost of that edge. So there we're going to stop. And then the final graph will end up being something of picking n minus 1 of those edges. So I get a total cost then of 2 minus epsilon, because that's the edge length, times n minus 1. But optimally, we would have simply connected it to the middle, which have given us a cost of n. So that gives us a bound of essentially 2. Can we do better? Yeah, that's a great question. We don't know any better approximation factor. So there's no better algorithms known. The integrality gap is known. So that is 2 minus 1 divided by n, meaning there's no hope in finding a better algorithm based on linear programming, so based on duality or LP relaxation. But there could, of course, be a different approximation. What is known, we know that the problem cannot be approximated within a factor of 1.0105, but that's, of course, still very far away from 2. And that's all I wanted to say about the Primal-Dual method applied to the Minimum Steiner Forest problem.